Good day. I'd like to introduce you to problem solving via LeetCode. I'm using pretty primitive recording technology. I'm going to try to keep it reasonably brief, but I want to go through a few iterations of solving a nice simple problem. If you haven't heard of LeetCode, I suggest you check it out. So I'm just going to make some notes here. So LeetCode.com. So make an account, and then when you're all logged in, select problems, and then in the column that's difficulty, select the easy problems, and then they'll appear just in the order that the problems were created. And then if you want to do the problem I'm doing today, select the first one, which is called two-sum. So you can see here that it's called two-sum. Now, LeetCode is a website designed for adults who are going for job interviews that require coding, allowing them to get some practice. But I'm sure we can find some good problems for students as well. And really nice thing is, once you've selected a problem, it's an all-in-one package. You've got the problem here, you can look at a solution there, but we won't do that. Submissions we'll talk about in a moment, and there's a discussion board too if you need to get some hints or something. There are hints down here, similar questions, so there's really quite a wealth here. But the important thing is the problem is given right here. That's all this one requires for description, and then the solution's given here. You can select a language and it gives you a template for the solution, so it supports a bunch of languages. I'm going to use Python 3. Now, what it provides you here is on the one hand simple and on the other hand complicated. So let me explain. The simple, well, we don't have to read or read input or write output. A lot of competition tasks require us to read input from a file or from standard input, and then we have to turn that text input into something that the computer understands. And that's fine if you're experienced, but for a new programmer that's a bit of a roadblock. Likewise, we don't have to write output. So how does it work? Well, all we have to do is implement this function, and the input is given to us as a list. I'll talk about the problem soon. The input is given as a list and an integer, and our function has to output a list of integers. This is a very new feature of Python that you can declare the types. I think it gets ignored, and we could actually remove this and it would still be valid. Okay, so that may look more familiar to you. The self, well, this is now how it went to. This was simple, now about the complex. You have to implement a function, which I don't think is a big deal, but a lot of people do. So we have to implement our solution in the form of this two-sum, and it has to be in a class. Okay, and so novices don't tend to understand classes very well, and not functions either. But I actually think that this is actually a really good way to get used to functions, and I'm going to demonstrate that. So I'm going to remove that now, and I'm going to recreate the default. Probably have to delete it first, because I think that those types are a good idea. Right, here we go. Oh yeah, the self is only there because this is part of a class. We can completely ignore it. It's an unfortunate, it's sort of I don't know if it's a deliberate or not part of Python's design. I don't really like it, but we can ignore it, and I can explain it another time. Anyway, let's talk about the actual problem. So given an array of integers, return indices of the two numbers such that they add up to a specific target. You may assume that each input would have exactly one solution, and you may not use the same element twice. So here's an example. If that's your list of numbers, 2, 7, 11, 15, and your target is 9, then 2 and 7 add up to 9, but you don't return 2 and 7, you return 0 and 1, because those are the indices. So, what we can do here is if I pop up the console down the bottom here, and by the way, just to talk about LeetCode, here's a list of problems, so I can chop and change between problems without leaving this screen, which is wonderful. So in the one environment I can select problems and work on them. And then working on a problem, well, here's a test case and it corresponds exactly to this example. And so if I do a really basic solution, return 0, 1, then I can run, I can go down the bottom right. Now there's run code and there's submit. Run code just runs it against the one test case that is given, and we'll get the answer, and it says accepted. All right, here was the input. My output was 0, 1. All right, there it is, and the correct answer is 0, 1. So this, you know, I've succeeded. I've succeeded for this particular test. If I change the test case, so 2, 7, 11, 15, and if I make it say 22, so 7 plus 15 is 22, and I hit run, then this is going to fail because my output is 0, 1, but the expected answer is 1, 3. So obviously this implementation didn't get very far, but if you're working with a novice student, then we've already learnt that return means provide the answer, and that's a good thing. And we've seen what a right and a wrong answer looks like down here. If I press submit, yeah, okay, I'll do that now. If I press submit, then it's going to run it against a number of test cases, and it's going to fail because I've returned 0, 1 as I've hard coded it here, but the expected answer for this is 1 and 2 for the correct solution. Click on details. No, I'm just going to ignore that. Okay, so all right, let's get going to a better solution. What would a better solution look like? Well, I want to imagine that we've got an input of 3, 8, 1, 5, 2 and a target of I'm going to say 13. Now, what we can do is we can, I'd like to be drawing this on a whiteboard rather than typing it in here, but hopefully you get the idea. If we can consider a table of these things added together, we're looking for two things that add up to give the required answer 13. So 3 plus 3 is 6, 3 plus 8 is 11, 3 plus 1 is 4, 3 plus 5 is 8, and 3 plus 2 is 5. We haven't hit the target of 13 yet. You can see though that it's going to come up here pretty soon. So 8 plus 3 is 11, and 8 plus 8 is 16, and 8 plus 1 is 9, and 8 plus 5 is 13, and we don't need to calculate any further. So this is an intuitive way of going through the all possible combinations. So what I need two indices to go through the list. It's the same list, and I need two indices to go through it. If I need two indices, I'm going to call them I and J. So I, well, that's going to be 0, 1, 2, 3, 4, and J down here is going to be 0, 1, 2, 3, 4. And then when we get the correct solution, then we've got I equals, well, I equals 3 and J equals 1, or something like that. So hopefully that makes sense, and that I'm now going to write code that will go through the list with two indices. So I can say well, first of all, I'm going to change my test case, and that's another nice thing. You can change your test case. So 38152, and my target's 13. All right, so I can make it exactly as I like. And now I'm going to say for I in range 5, that will mean that I goes through the values 0, 1, 2, 3, 4, and I'll say for J in range 5, and then I can say if nums I plus nums J is equal to the target, then we've found a solution. So I just return I comma J, and there we go. That's it. I'm pretty confident that this will pass this particular that this will get a correct result for this test case. Okay, so output was 1.3 and the expected output was 1.3. Okay, very good. Now you don't need to be a genius to know that this is not going to work for everything. If I press submit, then it's going to fail because not all lists are of length 5, right? So I can change that easily, and I could have done it up front, but I'm working on a principle of just doing as little as possible each time. So N, in informatics problems, it's common for capital M to represent N to represent the size of the data. So N is the length of nums, and then I can just say range N and range N. Okay, so I'll submit again. It's also not going to work, but for a different reason. I wonder if you can work out why. And if you feel that it's a bit slow, it's because the website wants you to pay for a premium subscription, which is fair enough. Okay, so in my submissions, this same data set 3, 2, 4, 6, and I gave the output 0, 0, but the correct answer is 1, 2. So why did I give 0, 0? Well, because I've chosen 3 and 3, because 3 plus 3 equals 6, and you can't use the same number twice. Okay, so yeah, I mean, what's happened here? It's obvious, but there's still a value in me writing it out. All right, so it's gone the 3 plus 3 equals 6. Yeah, okay. And so it found this answer immediately. So what can we do about it? Well, what we can do is make sure that we don't return the same index. So if I is not equal to j and the sum is correct, then return ij. So I'm going to run code and see how we go. Pretty confident that it'll pass this wrong and get past this wrong answer. Oh, I did run code. I need to do submit. There's a history of the submissions here. That's because I've done this problem before and I've explained it to students before. Okay, now we don't have a wrong answer anymore, but we do have a time limit exceeded. And the input, we can't see it all here. I'd love to show you, but I'm using a primitive screen recorder, which I think will not like me changing tabs. But if you do this and you click view all, then you'll get an absolutely enormous amount of data, many of which are 4 and 5 digit numbers, and you need to find the correct sum. So basically what I'm doing in this algorithm is too slow. It's too slow. And so one thing I can do is I can cut down the amount of work that gets done by First of all, I should never be considering 3 and 3. I should not consider that. I'll put a dash there. When I is 0, so I'm looking at this 3 here, then I should only look at the 2 and the 4. I should only look at j's that are greater than I, and I can make that happen very easily. But let's just see what that happens. 3 plus 2 is 5, 3 plus 4 is 7, all right? And then now, well actually, it's the I here that's I is 0. Sorry for confusing, it's much easier on a whiteboard, but you can see that the outer loop is dealing with this, and the inner loop is taking each one. So let me try to explain again. So the outer loop, when I is 0, j equals 0 just does not get considered. We just consider j equals 1 and j equals 2. Now I equals 1, we only consider j equals 2. So 2 plus 4 is 6, and there's the solution that we need. So for I in range n, yes, because we need to go all the way down, I think you can probably see that we'll never actually consider the last one, but I'm just going to leave it in range n. Now for j in range I plus 1, comma n, what that means is it will start the j one more than the I. So as we go through the data, we're actually considering less and less stuff. So that means we're doing less work than before, and maybe, just maybe, by the way I doubt it, but just maybe, we can get past this time limit exceeded. Because we're halving the amount of work, but if you've got a time limit exceeded, and once again, sorry, I hit run code accidentally. If you've got a time limit exceeded, then halving the amount of work is often not enough to make a difference. You need to do more like 1/10 the amount of work. But anyway, it says I was successful. All right, so I shaved off enough work to be successful. So now let's look at what success looks like. It took 7,000 milliseconds, so about 7 seconds, to do all of the tests. I don't know how many tests there were. And it was faster than 5% of all submissions for the same programming language. So that means it was slower than 95% of submissions. So I may have passed the test, but I'm still slow. So I'm going to show what I've done with students. There's a couple of ways to speed this up. First one is rather than working through all of the sums, we take a higher level look. So I'm gonna say I'll start with a comment. Okay. For some reason 38152 is my favorite example. So, and the target is, it can be 13 as it was before. Now, what we want to really know here is, right, so here's our I, looking at I equals 0, looking at the 3. What we really want to know is, well, we want a target of 13. I've got a 3. What I want to know is there a 10 anywhere in here? And the answer to that is no. Okay, and so now the I is moved on and points to the 8. And the complement, I like to call it, the complement of 8 is 5 to make 13. And so the question is there a 5 anywhere? And the answer is yes. And the index of the 5 is index 4. Okay, and so basically, here's a rough algorithm, right? Okay, so for each value of I, is there a value, first of all, for each value of I, calculate the complement, and then does the complement exist in the rest of the list? Don't look through the whole list, in the rest of the list, right? Okay, and if so, get its index, which we can call j, and return ij. All right, there we go. So I can achieve that with a Python command, a Python method called index. And I wish I could just demonstrate it rather than have to write a program in it, because demonstration is good. But I don't think I have a playground here where I can just do arbitrary code. Well, maybe I'll just write an arbitrary bit of code here and see what happens. So if I have my L equals 38152, then I'd like to know is there an index. I can say, let's say I equals L dot index 1 and J equals L dot index 2. Now they add up to 3, so that's not the right answer, and I'll just return IJ. But I'm just demonstrating absolutely elementary use of the index method. So the index of 1 is 2, and the index of 2 in that list is 4. Okay, and if I just run the code once, clearly it's not working, but the output is 2, 4, right? It's as I expected. Now, you can give index you can ask for, say, give me an index of 1, but it has to occur after index 1. And give me an index for the value 2, but it has to occur after the index 1. And these won't change. What I'm saying is you can provide a starting value at which the search takes place. So it's still giving me 2 and 4. But what gets interesting is if I ask for the index of 1, but it has to be after, well, even 2, no, I'll say after 3, there is no value 1 after index 3. Look, 0, 1, 2, 3, 4, right? There's no 1 in that part of the list. So this is not going to give an answer. What will it give? Let's see. Maybe it could give -1, maybe it could give none. As it happens, it gives a value error, right? So this is a bit awkward to teach to novices, and I think it's a poor design of Python. I don't think it's an error for a value not to be in a list. I think it should just be returning a special value like none to say that there is no index. But Python has a lot of poor decisions in it, and of course a lot of those are a matter of personal taste, so I don't want to be too critical, but in my opinion Python has a lot of poor decisions. So if we are asking for an index and it might not be there, we need to allow that an error can occur. So I can say try and say I equals L dot index. Let's say I get the index of 5 starting at 1. Okay, that will succeed. And J equals L index, and let's say I want to get 1 starting at 3. Okay, that will be an error. And then all going well, I'm going to return IJ. And what you do is you say except, because this is called an exception. So in the broader programming language community, these errors are called exceptions, and so that's why we've got the keyword, but then Python can't help itself, it calls it error here, so it's not consistent, but whatever. Alright, if a value error occurs, then this code gets executed, and let's just say we'll return a dummy value of -1, -1. And so if I run this code, then the output's going to be -1, -1. Alright, the output down the bottom is -1, -1. And incidentally, if I ask for something that is valid, so starting at 0, which is the default place to start anyway, then that will be a 2. And so now there'll be no value error that gets caught, and we'll return 3 and 2. Alright, there we go. So I'd rather we were able to write if l.index4 equals none, right? Okay, but we can't. I'd rather we were able to write that, especially in explaining it to beginning programmers. So that was quite a long aside, and now I can show you how we can speed up our program. Remember that we already have a successful submission, but it's at the slower end of the scale, and for education's sake we'd like to see what you can do to speed it up. So as before, n is the length of numbers, and for I in range n, what we can do is try to find, so here's our algorithm, calculate the complement. Well, let's get that. Complement equals the target minus nums I. Alright, so we've calculated the complement as shown here, and now we're asking, does the complement exist in the rest of the list? So we're going to use index, so we need to start with try, and we'll go j equals l index, and we want to start at I plus 1. We want the rest of the list, and no, sorry, we're looking for the complement, and we start at I plus 1. Okay, we proceed as if that was successful. If that was successful, what do we want to do? We celebrate and we go return ij. We've found our answer. And if an error occurs because the complement can't be found, then we don't want to do anything, but we have to tell Python we don't want to do anything, so I'll just say pass. I suppose I could say continue, or to continue the loop from the beginning. Anyway, I'll just say pass. That's Python's way of saying there's no code here. I like that Python has something to say that. Okay, so let's just run the code on one thing and see if we get a correct answer, because I may have some accidental error in there. Yes, I have. The name L is not defined. There you go. Right, nums. And running again. Okay, passed, and now go submit. Okay, so it's succeeded. A lot faster this time, 840 milliseconds rather than 7,000 milliseconds, and it's faster than 26% of all submissions. So it's faster than before. We're going to make it a lot faster yet, but I thought this was a good interlude, because basically we've made it faster, but we're really doing the same amount of work. The code before looked through the rest of the list to see if we could find a value that would add up to the target. This one, what does it do? Well, this line here, it looks through the rest of the list to see if it can find the complement. So why is it faster? Because Python is doing this under the hood for us rather than us doing it in Python. So Python is a slow language. That's not a criticism. Python is a slow language, and when we wrote the code ourselves, so for j in range n, whatever, and if, right, then that's executing a lot of Python code. But this line of code here that's highlighted, Python's doing that under the hood, and that means it's being done in the C programming language, which is a fast language. So it's doing the same amount of work, but in a faster language, and that's why we've got a faster solution. So we have not changed the algorithmic complexity of what we're doing. Basically, if n equals the size of the list, then we do something like n squared operations. Now, it's about half of n squared. If you've seen me try to draw it out with a grid before, and if you filled out every value, that would be n squared, but because we get a triangular arrangement, then it's half of n squared. But when you're talking like about algorithmic complexity, we don't care about coefficients like half or 5 or even 1,000, right? What we care about is the power, or like it could have been the square root of n squared or the log of n squared or what have you. But we do something like n squared operations. That is written like that, big O n squared, and just pronounce order n squared, or this is a quadratic complexity algorithm. And quadratic complexity algorithms are fairly slow, and we're about to do something faster. The same idea remains, right? Does the complement exist in the rest of the list? Well, so far, this is getting technical, but students need to be okay with technical stuff. For each value of I, that's order n right there, okay, because there are n elements. So for each value of I, calculate the complement. That's an instantaneous thing. Does the complement exist in the rest of the list? Well, that is order n. And so for each order n loop, we're doing order n work. That's where the order n squared comes from. What we can do is change this to order 1. Does the complement exist in the rest of the list? We can set up a special data type so that we can get a quick answer to that rather than getting a slower answer. Okay, so the description of the algorithm doesn't change one bit. We're still calculating the complement, finding if it exists, getting the index and returning it. So need to demonstrate a dictionary, or what I'll do is I'll demonstrate it like this, right? So value index. What we want is a table that looks like this. So the value 3, 8, 1, 5, 2. Okay, the index of 3 is 0. The index of 8 is 1. The index of 1 is 2. The index of 5 is 3. And the index of 2 is 4. Alright, for the list 38152, this is a correct table, right? The thing is, a Python structure, a Python type called a dictionary gives, it's like creating a table, and it has very fast lookup. Alright, whereas calling .index before is a linear search. It's looking through each item to say, is this it? Is this it? Is this it? A dictionary, it has a special way of storing its information so that it can find it very quickly. So, how do we do this? Well, we need to create the dictionary before we do any looping. So I'm going to call this index of, because it answers the question, right? What is the index of a value? And there we go, that's an empty dictionary. And I can say for I in range n, I need to, okay, so I guess should always put that as the first thing. Alright, so for I in range n, all we're doing is storing in the dictionary. So the index of, okay, I'm going to be really explicit here. I've called them value and index down here, so I'm going to say value equals nums I, index equals I, that's what I is for, index, and now we store it. The index of value equals index. Okay, so the effect of those 4 lines of code is that it will create that table and give us quick lookup. All right. Now I've been very verbose with the code, so I'm going to change it. I'm going to cut that down. Okay, I'm cutting this down to 3 lines. Okay, and so now we can go through our list, we can calculate the complement, get rid of this try and except, and all we need to know is, does the complement exist in the index of dictionary? So if complement in index of, so that's a yes or no, a true or false. So if it's in there, then we'll get it out. J equals index of complement. All right. So now we've got it, and we can return ij. All right, done. I can't run this code because there's all this stuff here, and I do want to leave it for a further discussion. Now, when I run it, I'll run it here and against our one test case and just check that things are okay. Yes, they are. When I submit it, there's going to be a problem. See if you can think of what the problem is. Maybe you have already. And it's our old 324 returning the 00. Okay. So when I went from the index solution to the dictionary solution, then I've reintroduced the possibility that you would find the same value twice. So I need to put another if in here. So if I does not equal j, then and only then do we return it. So the code's become more complicated. Right? The code has become more complicated, and that's just a thing. If you want your code to be faster, then it might need to be more complicated. Okay, so I'll submit now. Not expecting any problems. All right. So now the runtime, it was successful, and the runtime is 40 milliseconds, whereas about 800 milliseconds before and 7,000 before that. So we've really slashed the runtime, faster than 98% of all submissions. Now there's a bit of variability in these. I could probably submit it again right now and get a slightly different value here just because of external factors, and then this percentage would be different, but it probably wouldn't be less than 90%. So by pre-creating a lookup dictionary, then we're able to then make use of it in order one time, which means that the overall solution is order n. Now, I'll just make a little note here, and looking up a dictionary, depending how the dictionary is created and stored behind the scenes, is either order 1 or log n. And if you know anything about logarithms, and you know that they tend to make numbers very small. This is log base 2 here, but that doesn't matter. So log base 2 of 1,000,000 is 20. So if you can look up 1,000,000 items of data and then find what you want in only 20 steps, well, that's a very, very good outcome. And so overall, our whole algorithm is either order n or order n log n, and either way, very fast. Now, it passed everything, but I want to make one more point. It's possible, we just haven't encountered it yet, but it's possible that you can have data like this, 4514, and the target's 8. Now where's the 8 coming from? Well, the 4 and the 4. And if I run the code, it's going to be successful, but you might think, well, you're storing the index of each value, but there are 2 4s in there. You can't store 2 indices for the 4. And that's true, and it also doesn't matter. So it's successful. So maybe I'd be better off if I went back to my favorite, 3, 8, 1, 5, 2, and then put another, I was meant to say 3, 8, 1, 5, 2, and then put another 8, and the target can be 16. Okay, it's going to return the right answer, and we're going to have a think about what the dictionary looks like and why it's giving the right answer. Okay, correct answer. So 38152, and here I'll just put another 8. Now, the value at the index of the second 8 is 5, but you can't store 2 at once. The key, it's called, that looks up in the table, 8 is already there, and so that replaces the original one. And so this is what our for this data, this is what our index of table looks like. So we've got 3, 1, 5, 2, 8. The order of these is completely immaterial, by the way. When you put things into a dictionary, you're not guaranteed what order they'll be in. A footnote applies to that comment, but it's not worth saying that here. And okay, and so the indices are 0, 2, 3, 4, 5. So the original 8, which was in the dictionary for a short time with an index of 1, well, it got clobbered once there was another 8 and had an index of 5. And if there were more 8s, well, that would get clobbered as well. So why does the program work? Because we go through the list from left to right, storing the indices, which means that if there's a later value, it clobbers an earlier one. And so what ends up in the table is the final index, the rightmost index of any number. And then when we go through the list again, trying to actually solve the problem, we're going from left to right. And when we ask, when we have the first 8, and we ask, is there an 8 in here? It says, why, yes, there is in index 5. So our I is at 1, and then the J comes back at 5, and they're not the same. So it's because we're going from the left to the right, but the index, the index of dictionary stores the rightmost one that it works. Final comment. You'll normally see dictionaries written like that. That's with the curly braces. You can put values in here. So John is 43 years old. Sally is 38 years old, and their children, their child Tom is 13 years old. There you go. So that's a dictionary. The keys of the dictionary are John, Sally, and Tom. The values are 43, 38, and 13, and you could have millions of items in this dictionary and look them up very quickly. It's a great thing. But anyway, that's an empty dictionary to start with, and everything will work. So if you look back earlier in the video, you would see that earlier submissions have much less memory usage. We are consuming more memory because we're building a dictionary. But the trade-off for that is that we get faster runtime. And that is a common trade-off in informatics, in problem solving using programming. You trade off speed for time. You trade off space for time. You consume more memory by creating rich structures that you can look up in order to get faster results. Okay, that is the end of this. Further problems, I can't really say much about them. I think the reverse integer one is not necessarily a great one for working with students, but a lot of these I'm sure would be. Merge to sorted lists I think would be terrific. Just by the name I can imagine what it's like. Square root of x, probably some kind of iterative thing, so yeah, very good programming. Not all of them will be informatics style problem solving necessarily, but I hope you can see that it's a very good environment in which to practice programming. Okay, hope you enjoyed the video.